My name is Max. I am a postdoc at the University of British Columbia, and today I want to talk about mentoring undergraduate students. I'm going to talk through my perspective and through my experience. Right now I'm mentoring a couple of undergraduate students in the direction tensor decompositions, because tensor decompositions as applications, they show up almost everywhere. And whenever we think about most geometric mathematical objects, you always ended up somehow to think about tensors. So let me show you just notes and what we talked with my student last time. So first you can see the way how I organize my board. You can see it's pretty chaotic, I guess. At the same time, I'm trying kind of to separate into separate regions some of the facts or examples that we do. First advice, whenever you discuss something, if there is some small facts that needs to be checked or written down, I leave them as a homework. So in this case, you can see we have like 1, 2, and I feel like 3 homeworks. And I ask my student to take a picture of this board, to come home, and within the next week, to write the notes, what we have talked about, and also write these homework problems as exercises. So even if they will not have time to finish these homework exercises right away, they going to have them like written in their notes, so they can come back in like in a week or 2, or like, I don't know, even later, because some of them might be not be possible to answer right away, so they will need like to take some extra classes. So one of the example that we talk about, whenever you're going to take a vector in R2, so we're going to just take this vector, then what we can do with this vector, we can take the dot product with xy component and square it. So in other words, if you're going to take vector, let's say like 1, 1, then you will have x plus y squared. And what you're going to have x squared plus 2xy plus y squared. And you can think about the coefficients of this quadratic form as being a point in 3-dimensional vector space. So right now you take the point in 2-dimensional vector space, which is given by the linear form. So in this case, that will be just coordinates 1, 1. And you will map this to a point in 3-dimensional space where you just take your linear form and square it. The main question is, if I'm going to take this vector, act by some matrix A, and I'm going to map this vector to some another one for invertible matrix A. But if I'm going to do this right now procedure when I'm going to act by this matrix and square it, then I want to know, like, I know where my V1 is going to be mapped in terms of basis of this vector space to a new vector. But the question is, like, what is going to be the corresponding matrix in the 3-dimensional case? If I start with this vector over here, I act by the matrix over there and then map to another vector, then what is going to be the matrix which sends my original vector which I started to the ones which were mapped after acting by my matrix A in my domain over here. And that's one of the example of a homework problem that I gave to my student. So just to summarize, pick some topic that you're tangentially interested and want to learn more. Just apply to DRP program, or just coordinate with your graduate fellows and try to organize a DRP. And send out these applications to undergraduate students. And yeah, just get some people who might be interested to learn more about like algebra, analysis, probability, and even like more CS-oriented, I guess, math topics. And then just pick the article, pick the paper that you want to read, start to read together that paper with your student, and just discuss it on a weekly basis and enjoy it and learn something new. You can take this as a motivation to try to go and in your university and you want to learn something more, to learn something outside of your scope or learn something tangential to your research. Then we have a directed reading program when graduate students mentor undergraduates. And I strongly recommend like go and experience that, because it's like one of the best feelings in the world when you're learning something by teaching someone else some concept that you have no idea about, but your goal is like to learn on the fly because you're going through your PhD and you got some experience how to learn how to tackle difficult problems. So right now your goal is to teach the next generation how to tackle those problems. And the more you're going to do it, the better you're going to get in terms of mentoring and teaching. And the more you're also going to improve in your own field, because sometimes to improve in one field, you need to do some skills or some stuff which might not be directly related, but slowly digesting and trying to explain some complicated concept to someone else by guidance them. Somehow it's building some bridges in your like map of knowledge. and suddenly some problem that you had no idea how to solve, you will just realize and have a hint, have kind of a vision how to do it. For example, when you consider partial derivatives for multivariable function, then when you're going to take all nth order partial derivatives, you will end up with a tensor in the end, because a gradient is going to be just a vector, which is a combination of the first partial derivatives. Then you have a Jacobian, which is going to be a matrix, which is going to be like a symmetric matrix when you take a gradient and additional to the first derivatives, you're going to take a second derivatives. And this algebraic structure is going to get bigger and bigger and bigger the more derivatives you're going to take. So that's why it's really important to understand the geometry of such spaces. And we mostly understand the geometry of these spaces when we have degree 2. So in other words, when we deal with matrices. Because when we have a symmetric matrix, for example, you can construct a corresponding quadratic form. And to understand the space of all quadratic forms, you need to understand the space of all, really symmetric matrices. And one of the cool things that if you want to ask how many connected components I'm going to have for the space which is given by the space of all invertible symmetric matrix, then you can see that the number of connected components are going to be given by the signature of your matrix. So in other words, if you have n by n matrix, you can either have all eigenvalues are going to be positive or all eigenvalues are going to be negative, or you're going to have k positive and n minus k negative eigenvalues. So in total, you have n plus 1 choices for possible sign combinations for your eigenvalues. So that means you're going to have n plus 1 connected components. That's a really cool exercise. If you have time, try to do it. But as soon as we're going to jump from quadratic forms to the, let's say, cubic forms or homogeneous polynomials of degree 3, then suddenly everything just explodes. So that's why this is a great opportunity for an undergraduate student to go and explore something new, to see beyond linear algebra. And this is really hands-on experience, because it doesn't require much to jump from linear algebra to the next level. As the only thing that you need to do, you just need to have some extra practice with dealing with tensors, writing them down explicitly. Thank you so much for watching, and have a nice, great, good day.